In the early stages of a design, you lay down a grid of lines on a plan, and those lines become columns. It seems like one of the most straightforward decisions you can make. But get this wrong, and the consequences ripple through the entire project: awkwardly cramped spaces, blown-out budgets from deep transfer beams, or even a redesign after the foundations are poured. Sizing and spacing columns isn't just a structural calculation, it's a negotiation between the laws of physics, the economics of construction, and the poetry of architectural space. So, let's establish the rules of that negotiation. First, let's talk about what dictates a column's size. The primary job of a column is to carry axial load, the weight from above safely to the foundation. That load is the sum of the dead load structure, finishes, and live load people, furniture from its tributary area. The tributary area is the slice of floor that drains its load to that column. For a regular grid, it's the rectangle centered on the column. So, load equals dead load plus live load x tributary area. But it's not just about squashing. Columns also resist bending moments from lateral forces, wind, earthquake, or from eccentric connections. The material choice is huge. A steel column wide flange or HSS can be remarkably slender for the same load compared to a reinforced concrete column, which needs more cross-section to house the rebar and provide cover. Then there's slenderness. A very tall, thin column can fail by buckling long before the material reaches its crushing strength. The slenderness ratio, effective length/radius of gyration, governs this. A pro tip from structural engineers: for mid-rise buildings, concrete column sizes are often driven by minimum sizing requirements for fire resistance and rebar congestion, not pure load. You can't fit enough rebar in a tiny column, even if the math says you could. Now, the more strategic question: how do you space them? This is where architecture and economics collide. The spacing, or the structural base size, directly determines the floor system you use. Small bays, e.g. 6 to 8 meters, allow for simple, shallow, and cheap solid concrete slabs or metal decking. Larger bays, 8 to 12 meters, require more expensive systems like post-tension slabs, concrete waffle slabs, or steel beams with composite deck. The goal is to find the sweet spot, the largest possible column free space that doesn't make the floor system or the columns themselves prohibitively expensive. For offices, a 9-meter grid is often the economic optimum, balancing open space with efficient structural depth. For parking garages, you might push to 16-meter spans using pre-stressed double Ts. A common and costly drafting mistake is an irregular, inefficient grid. Every time you shift a column off the grid to accommodate a room, you create a cascade of different beam spans and loading conditions, increasing design time, fabrication complexity, and the chance for error on site. The spacing also dictates the size of the foundations. Double the tributary area, and you nearly double the load on the column and its footing. A few widely spaced columns might have massive, expensive pile caps, while a tighter grid distributes load to smaller, simpler footings. It's a systems optimization problem. Finally, coordination is king. The column's location isn't just a point on a structural drawing. It must align with architectural partitions. A column in the middle of a hallway is a disaster. MEP risers columns often house vertical ducts or pipes, and curtain wall mullions in them. This is where clash detection happens. The best column grid is one that becomes invisible to the end user, allowing the space to flow freely while quietly doing its job. In essence, column sizing is a calculation of strength and stability. Column spacing is an art of maximizing utility and minimizing total cost. One is governed by physics, the other by the value of space itself. A successful design masters both.